Welcome back, everybody. We're going to be continuing our lesson here on nomenclature, and I'm here on the Chapter 4 lecture note outline in Part C, which deals with converting a name into a formula. So we just learned how to do the opposite of this. What we learned how to do was look at a formula and determine what its name should be. Now we're going to go backwards. We're going to take a name and write a formula. Now, to do this, we're going to use this skill that we just developed in the previous lesson, which is balancing charges. Whenever we make these compounds, the charge has to be balanced to 0. So however many cations and however many anions we have, we add all of it up and it must sum to 0. Let's take a look at this first example, which is lithium bromide. As we can tell from the name, we have the elements lithium and the elements bromine in this compound. Now, lithium has a +1 charge, and bromine has a -1 charge. So this compound, together with just these two elements, has a neutral charge overall if we have one of each of these elements. So the formula would just be LiBr. Now, it's not always just a 1-to-1 ratio, of course. Sometimes we need more anions, or sometimes we need more cations to balance the charge out. Let's take a look at this in the next example. Here I have a compound called aluminum chloride. Now, aluminum is one of the metals that we learned has a fixed charge, and we learned it has a +3 charge. Chloride is a nonmetal in the halogens group, and it has a -1 charge. So if we have a -1 anion, and a +3 cation, how are we going to balance this out? That's right, we need more negatively charged anions to balance the +3 out. How many more? Well, we need a total of 3 negative charges to balance out the 3 positive charges. That means we need a total of 3 chlorine atoms. So our formula for this would be AlCl subscript 3. That's aluminum chloride. So a really common problem that we see at this stage is students will sit down to maybe do a problem on an exam or something in the lab, and they will need to have the formula, the accurate formula for a particular compound. Now, where the problem comes up is they're not able to write down the formula for a particular compound. And usually the reason why is they just don't know the charges on the metals or the nonmetals. So first, you got to make sure you have those charges down. You got to know the charges of fixed charge metals, and you got to know how to find the variably charged metals by knowing the charges of the nonmetals as well. So basically, make sure you have those charges down. All right, let's try the next example, which is chromium 3 nitride. Pause the video and see if you can come up with the right formula for this combination of elements. So first, we've got the element chromium, and then we have the element nitrogen. Let's write down the charges that we know about these things. Nitrogen is in group 5, so that's a -3 charge. What's chromium's charge? Well, chromium's a variably charged metal. I can tell that because, number one, I happen to know it, but also I can tell it from the fact that there's a parentheses here, and the parentheses tells me that chromium is a variably charged metal. If we're dealing with a fixed charge metal, these wouldn't be here. So anyway, we know that it's a variably charged metal. And because we have the charge here, we know also that the charge on chromium in this case is +3. So that's where we're going to start from. We have a -3 nitrogen and a +3 chromium. So if we're trying to make a neutral compound out of these two elements, chromium 3+ and nitrogen with a 3 negative charge, we just need one of each, and that gives us CrN, which is chromium 3 nitride. So that's the basic process that we use to write down the formula from a name. We have to know the charge of the nonmetal, and then we have to come up with the right combination of elements to balance the charge to 0. Now here in this next section, section D, I have listed some important exceptions or nuances to learn about nomenclature. Now, it might be a little unfair to call these exceptions. They're not really exceptions. They're actually more like extensions to what you already know. So additional information that you will definitely want to know when you're looking at things, and they might be a little bit confusing, so I like to put them in a separate area. The first is the difference between oxides versus peroxides. So when we say oxygen, that means the element oxygen. When we say oxide, that means oxygen that's been ionized. specifically with a 2 negative charge. That's the most common form that we see oxygen in when it ionizes, as the -2 ion. Now, there's another type of oxide. It's called a peroxide. And that little prefix, per, is actually shorthand for another word, which is hyper, which means more or extra. And what peroxide refers to is there are more oxygen atoms in this particular oxide. And what it looks like is oxygen with a subscript 2 and a -2 charge. So at first glance, it looks a lot like oxide. It has a -2 charge, but there are 2 oxygen atoms in it. And what that means is that each oxygen atom in peroxide is not -2, but -1. What's important for you to know is how to name compounds correctly as either oxides or peroxides. And I want to show you some examples of that below. What I'm going to do here is write out the formulas for these names, and then we're going to sort of dissect them to see why one might be called an oxide versus a peroxide. So the formula for sodium oxide is sodium with a subscript 2 followed by oxygen. And the formula for sodium peroxide is single sodium atom with a single oxygen atom. Let's take a look at why these are named differently. In sodium oxide, we have 2 sodium atoms. Sodium is a fixed charge metal with a charge of +1. That means we have a total of 2 positive charges. To balance that out in a neutral compound, the oxygen here needs to have a 2 negative charge. Because we're dealing with an oxygen with a 2 negative charge, that means this is an oxide. Let's compare that with sodium peroxide. In sodium peroxide, we have a single sodium atom. Again, that has a fixed charge of +1. To balance that +1 charge, there needs to be a -1 charge. The only way that can happen with a single oxygen atom is to have a -1 charge on that oxygen atom. So the formula for sodium peroxide is Na with a single O, and that O must have a -1 charge. That's the characteristic or defining feature of a peroxide, is that the oxygen has a -1 charge. Let's see if we can write down the formula for vanadium 4 oxide. If we're talking about vanadium 4 oxide, that means vanadium has a +4 charge. Now we have to balance that +4 charge with a -4 charge. And if we're going to do that with oxide, that means we need to have 2 oxides, because each oxide has a 2 negative charge. So that adds up to -4 charges to balance our 4 positive charges. So what's the formula for vanadium 4 oxide? That's correct. It's VO with a subscript 2 next to the oxygen. What about vanadium 4 peroxide? Here we have to balance out our vanadium 4 plus with a -4 charge. How are we going to do that with peroxide ions? Well, if a peroxide is an oxygen atom with a -1 charge, that would mean we would need 4 of them. We need 4 of them because each one is -1 and we need 4 negative charges. So our formula would be VO subscript 4. That's vanadium 4 peroxide. So take-home message about oxides versus peroxides. Oxides, you can simplify to having oxygen with a 2 negative charge, whereas peroxides, the oxygen will simplify to having a -1 charge. Now there's another one of these slightly confusing features, and that has to do with mercury. Mercury forms both +2 and +1 cations. As you might expect, the mercury +2 cation is simply Hg with a 2 plus up in the corner here to indicate that mercury has a +2 charge. Things get funny when we're talking about mercury 1. It turns out that mercury 1 is only formed when 2 mercury atoms are bonded together, as in a diatomic molecule. So if you want to picture mercury 1, this is a good visualization for it. We have 2 mercury atoms stuck together. Each mercury has a +1 charge. What would the overall charge of this entire bit be? That's correct. Overall, it would be a +2 charge, which is what's confusing about it being called mercury 1. We're calling it mercury 1 because each mercury atom in this entire thing has a +1 charge, even though overall it's +2. So the formula for mercury 1 is Hg with a subscript 2 to indicate both of those mercury atoms. But the thing is, we don't write a +1 up here in the corner because that's not what the charge is on the entire ion. The entire ion has a +2 charge, so we write that up here. This is how each of the mercury atoms can have a +1 charge only when there's two of them together. So mercury 1 has the formula Hg subscript 2 with a +2 charge, whereas mercury 2 just has a +2 charge on it. So that's the difference between oxides, peroxides, and mercury 1 and mercury 2. Let's go on to the next page. So far, what you've learned is that metals form positive charges and nonmetals form negative charges. In chemistry, there are always some exceptions, and one of those exceptions, the one we're going to focus on in this class, is the ammonium ion. The ammonium ion is the only cation that is a non-metal. And it's not ammonia, that's a separate thing, so don't confuse it with that. But ammonium is a special type of nonmetal. It's actually a group of nonmetals. So it's what's called a polyatomic species, a polyatomic ion, because it's a many-atomed ion. It has the formula nitrogen, and it has 4 hydrogen atoms in it, and overall it has a +1 charge. This is what's called ammonium. Ammonia, on the other hand, is a molecule. It's neutral. It has a single nitrogen and 3 hydrogen atoms. This is called ammonia. So we have ammonium and ammonia. Ammonium is the cation, and ammonia is the neutral molecule. Here's some examples with naming. The formula that we see here is NH4Cl. We name this with the ammonium cation in the front rather than nitrogen, hydrogen, and chlorine. We call this ammonium chloride because that's what it has in it, an ammonium ion with a chloride ion. We're treating this as a salt, a metal-nonmetal combination, even though ammonium technically is not a metal. Let's take a look at this next example. Here I have this ammonium ion inside of parentheses with a phosphorus ion. Now what I want you to do first is see if you can spot the error in this formula. There's an important error. First off, what's the charge of the phosphide anion here? That's phosphorus. If you look at phosphorus on the periodic table, you'll see it's in group 5, so it has a -3 charge. Now what's the charge on an ammonium ion? That's right, it's +1. So this is not balanced with just 1 ammonium and 1 phosphide anion. How many ammonium ions do we need to balance that phosphide? That's right, we need a total of 3 if each one has a +1 charge. That would give us +3 to balance out the -3 on phosphorus. And this would be the correct formula of ammonium phosphide, which is the name for the formula NH4 inside of parentheses, subscript 3 with a phosphorus atom. So that's ammonium, and it's the first example in here that you've seen of something called a polyatomic ion. Polyatomic ions are a small group of atoms, a collection of atoms that are permanently or close to permanently connected together. So you can think of them as a collection of atoms, a group of atoms that's stuck together. And your job is going to be identifying and naming polyatomic ions. You're going to have to learn 3 things about each of the polyatomic ions we learn in this course. You're going to learn its formula, its charge, and its name. And you're going to start by printing out the list of polyatomic ions that includes this information, making flashcards, and testing yourself until you're absolutely sure that you know all of these. Now, if you don't learn these now, it's going to be very, very difficult for you to complete some of the most basic stuff that we're going to do in the rest of this chapter and the remainder of the course. So you absolutely need to get these memorized as soon as possible. So with that being said, let's go on to the next page where we will take a look at that list of polyatomic ions and practice some naming with them. So I'm here at the top of page 13 in the chapter 4 lecture note outline, and you can see the polyatomic ion list for this course. This list is available on Canvas, and you will definitely need to print this out and then make up some flashcards where you have the name on one side and the formula and charge on the other. And then you need to know them sort of backwards and forwards. So if you see the name, you can write the formula, and if you see the formula, you can write the name. Now, just like you, I memorized this list a long time ago when I took a course similar to this one. And I can say when I memorized this list, it didn't take nearly as much time as I thought it would, and I was really glad that I did it because it made things so much easier. Now, also, as you're memorizing it, you will notice certain patterns that make learning it a lot easier. And if you need some tips on some of those patterns, I have a lot of them, so feel free to send me a message, maybe stop into office hours, and I'd be happy to share those with you. For now, though, what we're going to do is go on to this next section and practice naming compounds that have polyatomic ions in them. So let's take a look at how we name some of these compounds. And I'm going to start right up here at the top with the formula Na subscript 2 with a sulfur atom. So the first thing I want to do is notice that this is an ionic compound. I have a metal and a nonmetal. The next thing I need to do is figure out what's the deal with this nonmetal. Is it polyatomic or is it monatomic? That's right, this is just a monatomic nonmetal because there's only one type of atom there, sulfur. So I should just name this the normal way for naming ionic compounds. That is the metal nonmetallide way. The name of this metal is sodium and the name of this nonmetal is sulfur, but we change it to a sulfide. So we get sodium sulfide. Now what about this second example? What's different about this than the one we just completed? We have a sodium atom in it, and actually there are two of those. We also have sulfur, but notice there's something extra here. We have these oxygen atoms as well. You might be tempted to name this something like sodium sulfur oxide, but that's not correct. That's because this combination of nonmetals is called a polyatomic ion. In order to properly name this species, we need to know the name of this polyatomic ion. I happen to know it, but let's go take a look at the list above and see if we can find it. We're looking for a combination of atoms as SO subscript 3. So 3 oxygen atoms and 1 sulfur atom. So let's go take a look. So notice most of the sulfur ones are down here, and we see SO4 with a 2 negative charge. That's not what we're looking for. We're looking for SO3, and that has a 2 negative charge. So that's called sulfite. That's the name of our polyatomic ion. So what we need to do is go back to our name here and start writing down all of this information. Our metal is sodium, and our polyatomic ion is called sulfite. So this substance is called sodium sulfite. So let's look at this next example. It looks very similar. We have a polyatomic ion here, but it's a different combination of elements. We have 4 oxygen elements instead of 3. So where we found that SO3 was called sulfite, this, as SO4, is called sulfate. So we have the same metal here, sodium, and then a different polyatomic anion, and that's called sulfate. So this is called sodium sulfate. As you will see when you start memorizing the polyatomic ions, there are a lot of combinations of ate and ite. We just saw sulfite and sulfate. There's also nitrate and nitrite, and chlorate and chlorite. Now, one thing that might help you when you're learning these is that the ate version of the name has 1 extra oxygen in the formula. One thing that used to help me remember this was I would imagine that the ate ion somehow ate an oxygen atom, and that's why it has 1 more. So hopefully that helps out. Let's try another example here. We have magnesium and chlorine. Notice here, chlorine is just a monoatomic ion, so the name for this would just be magnesium and chloride. Now, the one below it, however, has a polyatomic ion in it. It has ClO with a 2 subscript. Let's go take a look at the list of polyatomic ions and see if we can find that. Notice that the polyatomic ions containing chlorine are grouped right here. We have perchlorate that has 4 oxygen atoms, we have chlorate which has 3, and we have chlorite which has 2. Notice that 8-ite relationship is holding true between these two examples. There's 1 less oxygen atom on the ite, and there's 1 more on the 8. So what happens if we add an extra oxygen atom? That's where we get this prefix per. Remember what I said earlier in this lesson? That per is short for hyper or more. That's what per does. Per means we add 1 more oxygen to the already 8 version of it. So we get perchlorate. So anyway, what are we looking for here? We're looking for ClO with a subscript 2. That would be chlorite. So let's go back down to our name and then we'll write it out. It's magnesium chlorite. So I can tell you when you get these polyatomic ions memorized, it's a lot of fun writing these names. Let's go down to the next example. We have barium with a polyatomic ion here, and that formula has oxygen and hydrogen in it. That one, if you take a look at the list, is called hydroxide, and it has a -1 charge. So we can name this barium hydroxide. The next one on the list has sodium and a polyatomic ion that has carbon and oxygen in it. That's called carbonate, and this entire substance is called sodium carbonate. And finally, we have the most interesting one of all, potassium with something called hydrogen sulfate. It's also known as bisulfate. So actually, we could write 2 different correct names for this: potassium hydrogen sulfate or potassium bisulfate. So there's an introduction to the polyatomic ions that we're going to use in this course. Now on the next page, I have a few examples of writing down formulas from names that have polyatomic ions in them. So let's go take a look at those examples. Now, as we saw on a previous page, it's necessary to not only go from formulas into names, but also from names into formulas. And both of these processes can be a little bit tricky. So we need to be careful with this. Let's take a look at how this works with polyatomic ions. Here we have a name for something called calcium phosphate. So it obviously contains calcium in it, and it obviously contains phosphate, but we need to make sure we get the correct formula. We can't just write down calcium and phosphate because this is not a neutral compound. Remember, we need to neutralize or charge balance all of our compounds when we write down their formulas. So let's take a look at this issue. First, calcium. We know that calcium, being in group 2, is a fixed charge metal with a +2 charge. We also know that phosphate has a 3 negative charge because that's one of our polyatomic ions. Now, what we need to do is come up with some combination of calcium and phosphate so that the charge does balance to 0. How can we do this if we have a 2 and a 3? Well, that's right. We need to have the least common multiple of these two numbers. That would be 2 times 3, which is 6. So we need to accumulate positive charges until we get to 6, and accumulate negative charges until we also get to 6, and then we'll have the right combination. So how many calcium ions do we need? That's right, we need to have 3. If we have 3 of them, and each one is 2+, that means we would have a total of 6 positive charges. Now let's go over to phosphate. How many phosphates do we need to get to 6 negative? That's right, we need 2. If we have 2 phosphates, each one is worth 3 negative charges, that would give us a total of 6 negative charges. And if we have 6 positives and 6 negatives, that balances out to 0. So what's our formula here? We have 3 calcium atoms, and we have 2 phosphate ions. Now how do we write this formula? That's right, we need to put the phosphate, because it's a group of atoms, inside of parentheses. And then we put the subscript 2 right outside, and we have calcium phosphate. So now that you've seen that once, let's try another example. And for this one, I'm going to give you the charges, assuming you don't have nitrate memorized yet. And then what I want you to do is pause the video and give this one a try yourself. Zinc is one of our fixed charge metals and has a +2 charge. Nitrate is NO3 with the subscript 3 next to the oxygen and has a -1 charge. So go ahead and see if you can come up with the right combination of zinc and nitrate and then write the formula down, and we'll compare once you unpause the video. So in order to write a balanced chemical compound for this, I need to make sure all of my charges add up to 0. What I've got is zinc with its 2 positive charges, and then I have nitrate with its 1 negative charge. Notice here that as they're written in this combination, we wouldn't add up to 0. What do we need more of? That's right, what we need more of is negative charge, and we can get that by introducing more nitrates into this formula. If we had 2 nitrates, that would give us a total of 2 negative charges. 2 negative charges would add to our 2 positive charges to give us a total of 0 overall, which is what we're looking for. So when we write the formula, we need 1 zinc and we need 2 nitrates. This is a group of atoms, so we put them in parentheses and then the subscript 2 right afterwards. So this is zinc nitrate. Okay, I think we should do one more example, but I want to change the example from the one I have written here to something maybe a little more challenging. So how about this? Let's try to write the formula for iron 3 sulfate. Iron has the symbol Fe, and we're talking about iron 3 here, so we'll have a 3 plus charge. And then sulfate has the formula SO with a subscript 4, and it's a 2 negative charge. That's sulfate. So I want you to go ahead, pause the video, and go about trying to write the formula for this combination. So first off, let's list out the components here. We've got iron and we've got sulfate. Iron has a 3 plus charge and sulfate has a 2 negative charge. And obviously these wouldn't combine together in a 1-to-1 ratio to have a compound with an overall 0 charge. So what should we do here? That's right, we need to find the least common multiple, which of course is 6 again. So we need to accumulate enough iron atoms to get to a 6 positive charge, and we need to accumulate enough sulfate anions to give us a 6 negative charge. And when we do that, we'll have 0 overall. So how many sulfate groups do we need to get 6 negative? That's right, we need 3 of them. If we have 3 sulfates with 2 negative for each one, that's a total of 6 negative charges. How many irons do we need to accumulate a 6 positive charge? That's right, we need 2 of them. If we have 2 irons with a 3 plus charge on each one, that means we have a total of 6 positive charges. Adding these up, we get a total of 0 overall. Let's write out the formula. We have iron and there are 2 of them, so that means we need to have a subscript 2 next to our Fe symbol. Next, we're going to write out our sulfate. This is a group of atoms and we have more than one of them, so we need to use parentheses to contain that group, and then put the subscript 3 next to it. This is the formula for iron 3 sulfate. And if you got that one right, definitely give yourself a congratulations. We've definitely come a long way since we started this lesson on nomenclature, and indeed since we started the course. So with that, I'm going to end this lesson. There's a follow-up video that you should watch after watching this one, and you've given yourself some time to memorize the polyatomic ions, and that's the practice worksheet video. There's a nomenclature practice worksheet and a video that goes along with it. You need to sit down and work through that worksheet. Maybe you get some, maybe you don't get very many, whatever it is, just do as much as you can and then watch the video to sort of help you along. I hope you're doing well. Please let me know if you have any questions, and I will see you soon.